Bismillahirrahmanirrahim. Assalamu alaikum everyone. So now we will be having our 9th lecture and we will be discussing NAND and NOR implementation. So normally whenever you talk about digital design, so our objective and motivation is that we must have a simplified expression and we should use the implementations that are universal. So as we already know that NAND and NOR, they are universal gate, and from the manufacturing point of view they are facilitating the design. So that's why we will be studying NAND implementation and XOR implementation whenever we are talking about digital design, right? So these are the bullets or topics which will be so these are the topics which we will be going through one by one: developing NAND circuits, and then how we implement the design on the basis of two-level implementation, and then if we can also have multi-level NAND implementations, then the utilization of XOR in XNOR, exclusive OR, and finally whenever we send and receive data, we normally follow some procedures from the point of view of, so normally when we send and receive data, so we have to adopt some procedures in order to detect errors, and today we will be studying one of the mechanisms for error detection, and that is parity checker circuit and parity generator circuit. So these are the bullets or points. So as we know that we have defined certain logic gates, and we just for sake of recap, we are having the gate in their truth tables. Here you can have OR, and this is the NOT, and we can also have a buffer, then NAND implementation or NAND gate in NOR, XOR. So just to have a recap, so these are the gates in their corresponding truth table. So here you can see that whenever we have one of the input is high, we will get a high, and when both inputs are high, we will get a 0, right? So 0 0 will get a 0 and both inputs, so either A or B but not the both, right? And here if you look at NAND, when one of the input is 0, we will get a 1. So this is a 0 sensitive gate, right? And if you look at the NOR, right, so whenever we have a 0 0, we will get a 1, and whenever any one of the 1 will cause a low output, right? So here if we have 1 at B, you can see 0, and we have 1 at A, we have a low output. So this is a logic gate that is 1 sensitive, NAND is 0 sensitive, and XOR, if we have to define in words, we can say that we will get a high output when one of the inputs are high but not the both, right? And these are the axioms, right? And some of them are represented graphically, and this graphical representation we will be using in a moment, right? So you can see that we have x dot y whole bar, and we have x bar plus y bar, right? So here we can have equivalent representation. This is the NAND, and what we can do, we can replace it with an OR but with inverted inputs, right? So this is NAND and this is the NAND representation but with inverted OR. This is NOR, but we can replace this with an AND gate but with inverted inputs, right? This is AND and we have the NOR but with inverted inputs, right? So here we have OR, you can see we have and an NAND gate, right, but with inverted inputs. So this is the NOT, right? You can place the bubble here or you can place the bubble at the beginning. So these are the equivalent representation of NAND. You can have both of them, right? So these are the DeMorgan's law, right? So you can see that we have pushed bubbles in some of the gate symbols, right? So here you have seen that we can replace this, right, with this AND gate but with inverted bubbles. So this is the famous DeMorgan's law, right? So we normally say that break the line and change the sign, right? So if I have to represent, right, so for example A plus B whole bar, right? So we normally say break the line and change the sign. So I will be having A bar dot B bar, right? So how I can represent, so this is the AND operation, right? I can write this as an AND operation but with complemented inputs. So if I have to represent it symbolically, so these are the complemented inputs, right? B bar and this is the AND gate, right? And similarly, whenever we have to represent AB whole bar, right? So what we will be having, so break the line and change the sign. So we will be having A bar plus or ORed with B bar. So this is the same, right? So we have A bar plus B bar. Alright, so and similarly what we can have A plus B, right? So this is equal to A bar, B bar and whole bar, right? So whenever we will break this exterior complement, so we follow the same principle, break the line, change the sign, so we will have a double bar, right, plus B double bar. So double bar, they cancel each other, so we are left with A plus B. So this is the equivalent representation. So how we can represent this, right? I can have an AND gate, right, with A, B, but with the bubbles, right? So what I did here, if I, right, this is B not A, right? So this is the conventional DeMorgan's algebra and we are going to use this algebra, right? So here is the mapping, right? If you want to map and OR to NAND, right? So keep in mind and OR to NAND, right? So here is the circuitry, right? So we want to convert that. So you can see we have an AND gate, and then OR. So this is AND OR logic. So we wish to convert that circuit, that logic to NAND-NAND logic, right? So what we can do, so if you look at here, so we have replaced this AND gate with this NOR but with inverted inputs, right? And similarly this AND gate with a NOR but with inverted inputs, right? And here we have replaced this OR gate with NAND but with inverted inputs, right? If you want to compute, you can always compute, right? Like if you have this similar output, right? So we will compute the input, right, when we will achieve our goal, that is mapping of AND OR to NAND-NAND, right? So then in the third step, so you always know that these two bars they represent double complement, and we know that this double complement, right, it will cancel out. So this double complement will cancel out, right? And you can see we have cancelled them out in the third step, right? So they are cancelled out and we are left with this, right? So if you look here, right, so this is what, so let me draw, right, so is, right, this is the AND gate, right, or you can say the NAND gate, right, and this is the NOR gate but with inverted inputs, right. So what we will have A bar plus B bar. So what I can do, I can close this, right, dot B whole bar. So these two statements, they are equal, right? So it means I can, and if I have the input A and B over here, so what will be the output? A dot B whole bar. So these two expressions, they are the same. So it means I can replace this, right? If I represent this OR gate, right, with bubbles, right, and I place AB here, so what this mean? This mean A dot B whole bar. So this is what? This is NAND, right? So similarly, we can do the same with this second OR gate with two complemented inputs, right? Right. So what we are left with, so after the placement, right, this is the NAND, this is NAND, this is already NAND. So we started from AND OR logic and we reached at NAND-NAND logic, right? So what we will be having, so after this third step, so this is NAND, this is also NAND, and this is already NAND gate, right? So we started from AND OR and we have reached NAND-NAND, right? And you can also have the Boolean expression of both these circuits and you will see that they are equal, right? So this is the mapping, right? So let's have a look. So we started from here. So this is A, right, A dot B, right, and this is C dot D, and what we will get, AB plus C D, right? So if I have the same inputs, A, B, and this is C, and this is D, right? Okay, so what I will be getting, A dot B whole bar, because this is NAND, C dot D whole bar, as this is NAND, right? And I will be having AB whole bar, right? And this is CD whole bar, and this, right? So what is the philosophy, right? What is the rule? So break the line and change the sign. So I will break the line, right, and change the sign, right? So those two bars, they will cancel each other, and we are left with this one. So you can see that if you compare this Boolean expression with this Boolean expression, they are the same, right? So this is a sort of verification, right? So here we have two-level implementation, right? Sum of the product and product of the sum, right? So you can see that if you consider the pronunciation sum of the products, so we have the first term at the end, right, while we are implementing. So sum of the products, right? So products are here, right, because these are AND gates and they represent the product, and this is the summation of the input. So after the product we are going to add them, or we are summing, right? So sum of the products. So here we have, you can say, change their places, right? So we have multiplication or AND operation at final stage, right? And we have the OR gate at the first level, because we are talking about two levels. So at the first level we have OR, and on the second level we have the product. So you can see product of the sums. So sum, and this is also sum, and then we have to product them all, right? So if you look at the representation, right, and you can always have an idea that AND gate forms the products, right? OR gate forms the sum. So sum of the products, and over here we have OR gate, right, for sum, and this is min terms, right, and this is the conventional representation, and we already have gone through this. And when we have OR operation, we say max terms, right? So min terms and max terms, right? So here we will be adopting the same sort of procedure, right, whenever we have to replace them with NAND. So here you can see we have AND OR logic, right? So we will adopt the same methodology. We will place the bubbles, or we can say we will push the bubbles, or we can say that we will push the bubbles. So you can see that we have placed two bubbles, and naturally they will not have any impact on the circuitry, because they will cancel out according to the Boolean axioms, Boolean laws, right? But we will achieve our goal of conversion, that we want, or we wish to convert that AND OR logic to NAND-NAND logic, right? So here we will place two bubbles, they will cancel out, making no impact, no difference, right? Here again we will place two bubbles, right, having no impact, right? So if you have the output before this bubble, right, let me give you an example, X, right? So after this bubble we will have X bar, and when we will come across this bubble we will have double bar. So they will cancel out, right? So similarly we have two bubbles here, they will cancel out, right? And what we will get, right? So you can see, what is this? We all know, right? So let me draw this, right? So we have the OR operation, right? three inputs, right? In those three inputs, they are already complemented, right? So we will place bubbles. So if we have A, B and C over here, so we have A bar, right, plus B bar plus C bar, right? So if I want to write them in compact form, so I can write them, right? Because whenever I will follow the axiom or DeMorgan's law that break the line and change the sign, so I will be having the same, right? So we can have AND, right, with inversion, which is NAND, right? And we have three inputs, right? A, B and C. So we will have A dot B dot C, right, with whole bar. So we can replace this OR with inverted inputs by NAND gate, right? So this is what I was explaining on the previous slide, right? So this is a two-level NAND-NAND. You can see that we have two NAND gates, first level, right, and this is the second NAND gate, right? So there are some tips that you should follow when you are converting between different forms, right? So first step is to introduce bubbles. That's what we did when we were converting from AND OR logic to NAND-NAND logic, right? So here again we can see the example, right? So each introduced bubble must be matched by a corresponding bubble, right? So we have introduced two bubbles over here, right, so that they are matched and they have no impact, they will cancel out. So then we have conversion, right, by using those inversions, right? So you can see we have this AND OR operation. We have placed two bubbles, they will cancel out, and finally we will get NAND, NAND, and this is also a NAND, right? So this is verification, so we can always have the verification by having the appropriate expression, right? So A dot B, right, plus C dot D, right? So I'm placing brackets, right? So if you compute this, so what we will be having, right? We have A, B whole bar, right, and then we have C, D whole bar, right, but they already are. So let's move to this part, right, that includes NAND, NAND, and this is also NAND, right? So this is also NAND representation, right? So we are left with, so if you want to draw this, right, so we have A, B whole bar, right, and we have C, D whole bar, right, and then we will be having double bars due to this, right, and they will cancel out, right? So AB plus CD, and that is the same Boolean expression or Boolean function, right? So here you can see that we have this, right? So we can perform this conversion, or we can achieve this conversion by following certain steps in a sequence. So here we are, right? So then we can easily achieve the conversion of AND OR logic to NAND-NAND logic, right? Conversion to NAND gates, right? So first, what you have to do, we will start from SOP, sum of the products, right? So then we will be simplifying the Boolean expression, right? So we also want to simplify the Boolean expression, right? And then after the simplification, next what we will be doing, we will be definitely drawing the circuit, right? So then we will draw the network, and here we have AND OR logic, right? And then after that, what we have to do, we have to push the bubbles, right? So we have pushed two bubbles here, one bubble here, right? And wherever we have AND OR, we will push two bubbles. So here we have only AND, right? So we only have pushed one bubble, right? So you can see that the line is more thick. So here we have placed two bubbles, so you can see, and here also, right, we have thick line because we have OR, so we have pushed only or placed only one bubble, right? So this is the second step where we will be pushing the bubbles or placing the bubbles, right? And then because we have placed a bubble here, so in order to balance it out, we have to add an inverter, right? Because that bubble along with that interval, they will cancel out each other's effects, so we will be having this straight line, right? So here we have the two bubbles, right? So they already are cancelling each other, right? So here we have to add another inverter in order to cancel the effect of this placed bubble or pushed bubbles, and you can see that we already have a bubble here, but we can handle it externally. So you can see that we have placed a bar here, so we can handle it externally. So over here it's the same, we can. So now we have the complete conversion. You can see this is the NAND, right? And this is also a NAND, because we can always have a NAND, right? We can always have a NAND with which can be replaced by, so you have A, so right, so A, right, so we have left with A bar. So this is an inverter, right? So we can always replace this inverter with a NAND, right? This is already NAND, and this is also a NAND. And OR with two complemented inputs can always be replaced by a NAND, right? So this is an inverter, and we can always replace this inverter with a NAND gate, right? Here again, OR gate with two complemented inputs, with two complemented Boolean inputs, right? So we can replace it with a NAND, right? Right. So let's talk about multi-level logic, because before we have talked about two-level NAND conversion, or so logic, right? So now we will be having multiple level logic. So you can see that we have different numbers. So I will not go into details regarding those numbers, but we can have an idea that here we have we need or we require lesser number of resources regarding the area, regarding the wires and the variables and literals, right? But over here we need lesser resources, right? If you look at the wires, here 25, here 10 literals, we have less literals, and the internal wires are also lesser, right? And the expression is the same, so you can if you multiply or if you want to compare this expression and this expression, they are the same, right? So then what is the difference? So difference is our arrangement. So here you can see that we have the factored form, right? So here we have sum of the products, so these are the products which are summed up, right? So sum of the products, right? So here we have the factored form, right? So this is the difference. So now let's move to the multiple levels. So if we right, have to convert into a multi-level NAND logic, right? So here we have first level, right? I declared this second level, third level, and fourth level, right? So this is the original network while representing AND/OR network, right? So here we have AND gate, OR gate, right? AND gate and then OR gate, right? So what we will be doing, we will be placing bubbles, right? So here we have two bubbles, right? So you can see that here we also have two bubbles, right? And this is the, and then what we will be doing, so here again you can see that we have placed two bubbles because this is AND OR, so we are placing two bubbles, and these bubbles will also cancel each other, right? So here you can place this with NAND, right? This is also NAND, right? So this output F and this output F, they have the same effect, right? But remember that we have to handle those inverters externally, so there is a change, right? So here we have B, or here we have a B complement, right? Similarly, here we have C, right? And here we have a C complement, right? So this is the difference, like we have to handle the complements externally, right? There is one difference, right, that we have to handle the complements externally. So here you can see that this complement is handled externally. So here we have a B, right, but here we have a B bar, right? So this is the difference, right? So let's have an example, right? We have the original circuit, right, and then we will push the bubbles, right? So these are the two bubbles, right? Right. So here you can see that this bubble, right, is having an impact over here, and then we have two bubbles, right? And then this is the bubble that is externally controlled or handled. So these two bubbles, they have to cancel each other, right? And those two bubbles, they also have to cancel each other, right? So this is an input, right? So we have to apply this input after the bubble. So we will be handling is this input externally. So we will place a bar over here, right? So these two, they will cancel out, right? And then we will be placing a NAND gate, right? An OR gate with complemented inputs can be replaced by a NAND, right? So there is a difference here, right? So that's what I have mentioned, that we have to handle this externally, right? So because of mismatching, right? Because there is a mismatch, right? So we will be handling this externally, right? Because this input is plain X, right? And but this, after this bubble, it has to be complemented, so this will not match with the original input, that is X. So due to this mismatching, we have to handle this externally. We can place, when we apply X over here, we will put a complement, or we have to complement it, this input, right? And then this is another example, right? This is a rather easier way, right? So we have a circuit over here, and we want to implement the NAND-NAND logic, or we want to convert that circuitry so that all the logic is NAND, right? So you can see, we can straight away place this AND with NAND, right? And NAND, right? Then inverter, right? So this is an AND. So here we can always place this with AND, right? With an inverter, right? NAND with an inverter. So this is an AND, right? Again, we always have an OR gate with the help of NAND gates. So here what we can have, right, if you look here, so I can, if I have right, so we can use this area, right? We have an OR, right, with two inputs, so this is C and this is D, right? So I will be having C plus D. So if I have this, right, C, right, D, right, so this is C bar and this is D bar, right? And then C bar dot D bar whole bar, so that is C double bar plus, break the line, change the signs, same, right? So we are left with C plus D, right? So we can place, right, this OR gate with NAND gates, right? So here again OR with NAND gates, this is AND, so we can use NAND with inverter, so it's AND gate, again AND gate. So this is the another methodology to, so what is the next, right? So this is interesting and this is something different, right? So you can see that here we opened up, right? So we have two bubbles, right? So these two bubbles, they can cancel out, right? And then we always have, so you can say that we can place a straight line, because those two bubbles, they will cancel out, right? Those two bubbles or bars, they will cancel out, and we can replace those bubbles with a straight line. So here you can see, right? And while we have already have the NAND gates, right? So this is the conversion, right? Now let's move to exclusive OR and exclusive NOR. So we can have the symbolic representation of exclusive NOR, right, and exclusive NOR, right? So this is exclusive OR, right? So you can see the symbolic representation, and we have the truth table over here, right? So you can see that whenever we have one of the input high, we will get a high output. When both the inputs are same, we will get the 0, right? So either A is high or B is high, but not the both, right? If you talk about the high inputs, right? And then we have the exclusive NOR circuit, right? So you can see that we have the same symbolic representation but with a bubble. So that represent the exclusive NOR. So if we talk about the simplification, we can also have XNOR in order to simplify the circuitry. So here we can see that we have more number of gates, right, here, and when we used or replaced them by XNOR, we got the lesser number of gates, right? Although this functionality, either XOR or exclusive NOR, they are basically built from the basic logic, Boolean logic, and or not, right? So you can, if you look at the expression, we can see that we have A, B bar, or A bar B. We have OR operation over here, AND operation over here, and the NOT operation or the complement operation. So this is the XOR, right? So we can also represent those XOR and XNOR functions with the help of, right, NAND gates. So here we have shown the XOR representation, but by using NAND gates. If you compute this Boolean function, you will see that this is the exclusive OR implementation, right? So then parity generation and parity check-ins. First, you should know that why we need parity generation and parity checking. So normally when we transmit data, there is a sender that is receiving the data, so there are chances that the data became noisy due to some circuitry or maybe due to some other problems, channel problems, or there are a lot of different reasons of noises. So you have to adopt certain mechanisms, certain methodology in order to first detect the error, and then there are some correction procedures, right? So here we will be talking about parity generation and parity checking in order to avoid the errors, right? So for example, if we have a data over here that we want to transmit, right? So you can say that we have 1, 1, 1, 1, all ones, right? So if you talk about the XOR operation, right? So you can see both ones we will get a 0 over here, and both ones we will get a 0 over here, right? And we will get a 0, right? So the parity bit will be a 0. So remember, we have all ones, right? And they are even, because for they are even and the parity is 0. And we transmitted that data on the transmission line, right? So on the receiver side, we must have a parity checker, right? So this original data we will receive, and this is the parity bit, right? So this 1 1 0 1 1 0, right? And we get 0 and 0 with 0. So if we get a 0, it means no error, the data is correct, right? If we get 1, it means that some of the bit is changed, so there is an error. So we can request the sender to resend the data. But there is a problem, right? There is a limit, right? If 2 bits are changed, then we will not be able to detect the error. So this is the limitation of this circuitry, right? So we can take another example where we have odd number of ones, right? Because this is an even parity generator, right? So let's have odd number of ones, right? So if I place a 1 here, right? 1 here, right? D1 0, right? And then 1 here, and then 1 here. So those two ones, they will produce a 0, right? And then those two ones, right, they will produce a 1, right? And then we have a 1 here, so this is the even parity. So you can see that when we are going to transmit, the total number of ones are even, so that's why we name it even parity. So number of ones over here in the original data are odd and the parity is 1, so total number of ones will be even, right? And over here we have the over here we have parity as 1, and this is the original data. If we start from 0, that D naught is 1, right? And that is 0, 1, 1, right? So now we have to verify. So 1, 1, 0, right? 1, 0, 1, this is 1, right? And this 1, 1, 0, so it means data is correct, right? So it means we have received the data safely, right? But if there is some error, for example, this 1 becomes this 0 becomes 1, so then now what we will be having, this 0, right? And due to this one, this is also 0, right? And this is also 0, right? And the parity is 1, so we will get 1, so 1 mean an error, right? So we have verified in both cases when we are transmitting even number of ones, and in other case we are transmitting odd number of ones, right? So that is the parity generation and parity checker, right? So that's all for today's lecture, right? So today we have converted AND OR logic into NAND-NAND logic, right? And we have used our old friend DeMorgan's axioms, right? And then we have different examples, right? And then from two-level implementation, we talked about multi-level implementation, right? Whenever we want to use the NAND gates, because they are universal gates, so we want to use NAND gates as much as possible, right? And then we have seen that how we can follow certain steps in order to have NAND-NAND implementation or conversion, right? And if you want to move from a Boolean expression, right, and then you perform simplification, right, by K-map, and then you can after simplification you can have the circuitry, and then you can apply the NAND-NAND logic, whatever the circuitry you got, and or not, whatever the circuitry you have, you can always have the NAND-NAND logic, right? And then we talked about XOR, right, and XOR, and the simplification by using XOR, right? Because we can always have simplification by XOR, and although those two Boolean logics, they are made up of the basic Boolean operators like AND or not, right? And finally we talked about parity generator circuit and parity checker circuit, and we emphasize on even parity generator circuit and even parity checker circuit. So that's all for today, right? So next time we will talk about another topic, right? So that's enough for today's lecture. So I will recommend you people to exercise, right, as much as possible, right, to solve the examples which are available in your textbook, right? So that's all till the next lecture. अपना, अपने दोस्तों का और अपने रिश्तेदारों का और गिरदो नवा के लोगों का ख्याल रखिएगा। अल्लाह हाफ़िज़, अस्सलाम वालेकुम।